Hi everyone, I'm Dale. I am the CTO of a local fintech company called Nominini and also a cloud developer expert for Google. I am a recovering mechanical engineer, actually. So I didn't start my life as a software engineer. I started as a mechanical engineer, but I always felt like I was maybe born 150 years too late. The golden age of STEAM and mechanical engineering was long past by the time I started, or I guess before I was even born. And these days, you have machines that are controlled by electronics, and those electronics are run by software. And so it's sort of this natural progression into software engineering over, I guess, my lifetime as an engineer. And these days, with Nominini being a fintech, it's entirely software-based. So I get to scratch my electrical engineering and mechanical engineering itch by developing some home automation stuff. So today I'd like to share some of that journey with you. And I'm going to be talking about the state of home automation, a little bit of MicroPython, some demos with some electronics, the ESP8266, and the various pieces of software that you can use with that. About 15 years ago, I actually started getting into IoT. In those days, I think it was GPRS was just starting off. Edge was maybe being rolled out by MTN across South Africa. If you wanted to communicate with a modem to get an internet connection, you had to do AT commands to do dial-up. And to do anything on a microcontroller was expensive and very time-consuming and pretty difficult. 10, 15 years later, that world has changed. It's now become accessible for anybody who doesn't have a degree in electrical engineering to be able to build something themselves with very little stress. You can start small and build your way up and get as much complexity in your life as you'd like. The challenge is there's a plethora of products out there. Something like the Sonoffs, which you can buy for relatively cheap. You know, it's got switches for lights. You've got wall mount switches, your smart bulbs, all sorts of DIN rail mount stuff. The Raspberry Pis and the ESP8266s, as well as all sorts of Google Home, Alexa, assistants like Siri with Apple, and there's tons of things. So where do you start? And I think the simplest place to start is just by buying a simple lamp that, if you want to control that, perhaps a desk lamp, you can get what's called the Sonoff Basic. And these you can buy from companies like Communica, which is in Johannesburg and Cape Town. They're an electronics store, and they sell these little switches for 120 Rand. And I've actually got one on my desk here, connected up to a lamp. So let me see if that, put that there. So it's my lamp. You then install some stuff on your phone, eWeLink, and Google Assistant. So let's see if we can do a very basic demo to show you how that works. I got my lamp there, opening up my Google Home app. And if I say something like, "Hey Google, turn on the desk light," the light comes on.
All right, turning on desk light.
And then I can do something similar. "Hey Google, turn off the desk light." So with this device, and no more skills than being able to wire up a plug, you can get some basic home automation going. And it's pretty cheap at 120 Rand. You can't really go wrong with that. You can also link the eWeLink app up to Alexa, but sadly not Apple. They're not big into the maker community, and so you'll have to stick with either Google or Apple. Alexa for now. One of the downsides is the Sonoff devices are on your local Wi-Fi network. They have to then connect over the internet to the eWeLink cloud servers that then run the Sonoff devices, and that then connects back to the Google data centers. EWeLink is a Chinese company, and Google is an American company, neither of which have in recent times been known for being privacy conscious, or at least overly privacy conscious. And of course, the downside is if the internet goes down, you can't use your lights, which is pretty inconvenient. So the next step is open source. Now, Sonoff devices are running, have a little microcontroller inside, the ESP8266, which we'll come back to in a few minutes. You can get open source software by Tasmota. So this is an open source project. That link down there you can get. This firmware, you buy a little FTDI USB to serial converter. So that basically takes USB from your computer, converts it through that little IC into serial. And those pins over there, you solder on some wires and you plug them to various places on the Sonoff board. And that then allows you to flash the Tasmota software onto the Sonoff device. So you get nice hardware, relatively cheap, but you can put your own software on there. And because it's open source, you can fiddle to your heart's content. You can then buy a Raspberry Pi. So the Raspberry Pi 4 that I'm currently using is about 1,000 Rand. You can then get the case and the heat sinks. Please, when you get these things, put the heatsink on. The chip does run a little bit hot. You don't need it, but certainly recommended. You can also put the fan in there into the case if you really want to, but it's nice that it's silent if you don't run the fan. And for home automation, you don't need that. And of course, then it's the power supply and the micro SD card. So it brings up the total cost to about 1,400 Rand. That then you can put Home Assistant, which is an open source home automation software, onto the Raspberry Pi, and that will communicate to Tasmota all over your Wi-Fi. So even if the internet is down, you can still switch your switches on and off. There's also a Home Assistant app for iPhone or Android, and that then allows you to control it. And that's all open source, so you can see exactly what's going on. If you want to, you can then connect over the internet back to Google Assistant, and that will then activate voice control. But that's kind of like a nice to have. At least if the internet's down, you can still switch on your lights and control, get all the readings from your home. But having voice control is really nice. So that software stack, what do you actually put onto your Raspberry Pi? Well, there's Home Assistant. Home Assistant is an open source application, pretty much made for hackers and makers. You can put anything you like on there. You can see that there's light switches here. There's a bunch of temperatures. You can then get the set your thermostat. Perhaps you want to put a map of your house and include passive infrared sensors and your alarm system wired into Home Assistant. You can control your music. You can get other sorts of information. It's not necessarily about your house, but it's important to you. And that then you can put onto a tablet and maybe mount it to your wall or have it running on your phone or your laptop. So it's nice central brains of your home. Next up, what stitches this all together is a protocol called MQTT. It's specifically designed for IoT. It's a very simple pub-sub protocol designed for low-powered embedded systems. So you might have some temperature sensors that then publish the temperature to the MQTT broker, and you have subscribers to that. And there might be a subscriber, Home Assistant might subscribe to the temperature topic. It will then do something, perhaps switch on a light or a heater by itself publishing something that then the Sonoff device subscribes to. And there's different sorts of brokers. The most popular one is Mosquito from the Eclipse Foundation. And that, is pretty easy to set up as well. So now you've got pub-sub running on your home network. For monitoring, there's Prometheus. For those of you who get involved with software at work, probably running Prometheus and Grafana. Prometheus is a time series database. It will get a whole lot of metrics about what's going on around your house and save them to a database that then can be queried by something like Grafana. So you can then get graphs and charts and alerts and all sorts of things. So you can get a nice dashboard overview of what's happening. And if you want to get a little more complex, there's some software called Node-RED. If anyone's played with Lego Mindstorms as a kid, you'd know that sort of that connection paradigm where you connect sensors and actuators together, and there are these little blocks in the middle that are for doing some sort of logic. Or if you've used something like if this, then that, the online service that stitches different surfaces together, Node-RED is similar to that. So in each one of these blocks is a sensor, and it might have output that's either debug or actuators that are output, and then you can write some JavaScript inside of any of these to perform the logic that you wanted to do. And it allows you to then make more complex workflows without having to do a lot of coding yourself. So in brief, the home automation software stack that I'm currently running is Home Assistant for home automation, Mosquito MQTT Broker for PubSub, Prometheus is a time series database, Grafana for visualizing that data, and Node-RED for flow-based software control. Of course, you're not going to be a modern software engineer if you're not going to take the DevOps mindset and treat infrastructure as code. And for that, Ansible is pretty good to use, quite easy to get started with. The way Ansible works is you have a playbook. So that is effectively describing what you want to happen. So how do you want to configure your nodes? And rather than just writing long bash scripts, there's a lot of little snippets of code that are out there for how to configure servers. So you paste that into a playbook. YAML, the language of love for the cloud is YAML. So you need to learn that and paste a lot of these bits of YAML into a playbook, give it a list of hosts, and Ansible will then provision those hosts for you. Or if you just got one, the Raspberry Pi. Why is it useful? Because micro SD cards are prone to failure. You get a maybe 64 gig micro SD card. They're made to go into a camera or maybe an MP3 player or something like that. They read and write to it a handful of times a day. If you're going to be plugging that into a single board computer like a Pi, that is going to really hammer those cards. And they fail a lot more often than one would like. And at least with having your stack set up via code, you can rebuild your Raspberry Pi if that fails, and you have minimal downtime at home. Combining that with Docker is a good way to make sure that you've got repeatable software running. There's many ready-made Docker containers available for you for home automation. They happily run on ARM architecture, which is what is on the Raspberry Pi. And yeah, you can just pull them down from Docker Hub. On my GitHub, I've got my home provisioning scripts or my playbooks, so feel free to have a look at that. And yeah, see some simple examples, but examples nonetheless. For those who don't know containers or aren't familiar with them yet, containers are a way of abstracting away complexity. The analogy and where container comes from is in the world of shipping and logistics. There's just these boxes that get moved around. Whether you put that box on a truck or a train or on a ship, the shipping company doesn't really care what's in that box. As long as it conforms to a particular size and a particular weight, that shipping company will send it for you. But you can put anything from wine in there to clothing to microcontrollers, whatever you want inside of it. And that analogy is then very similar to how Docker thinks about containers or how containerization works. You can put any software that you want inside of that. It's encapsulated in that container. And whether you're running that container on a low-end Raspberry Pi all the way up to the largest or extra large cloud VM, that container will run the same way. What it makes it nice for hobbyists, I think, is that you don't really have to worry about doing lots of sudo apt-get install onto your computer and trying to get the software working together, especially when there's conflicting libraries involved. So how do you containerize your application? Well, first of all, you take the infrastructure. In this case, I'm using a single board computer, the Raspberry Pi 4, and then you install an operating system. I'm just using the bog standard Raspberry Pi OS, used to be called Raspbian. It's just a type of Debian. So if you're familiar with Debian or Ubuntu, you'll be comfortable with Raspberry Pi. On top of that, install Docker. And for that, configuring my operating system and Docker, I'm just using some Ansible, the playbooks for that. And then you connect to Docker Hub and you start pulling the images. You can pull Home Assistant, Mosquito, MQTT Broker, Prometheus, Grafana, Node-RED, and whatever applications you want, you can then just run on your Raspberry Pi. Pretty easy to set up and get working. So I'm going to show you, there's a little visualizer, it's Docker Swarm Visualizer, which I'm also running as a container. It's a little web server. And so you can see what I'm currently running. So this is my 2 Raspberry Pis, Home Pi and Home Pi 2, both got about 4 gigs of RAM. And I've got Home Assistant, the Node Exporter, which is all the metrics about like CPU usage, disk usage, stuff like that. Node-RED, the visualizer, which is this little web app. My Time Machine for my Mac OS backups, Prometheus, and then on the other worker running Grafana, Mosquito, and another node exporter just so I can see what's happening on this machine. And then if any of these containers disappear or get rescheduled, this dashboard updates in real time. This is a nice way of seeing what's happening on your Pis. So let's get to the next level, building your own hardware. So I had a problem, or have had a problem for a long time, is I run out of electricity. The first time I noticed that I run out of electricity is when the lights go off. And of course, always blame ESCOM until I look over at my neighbors and see that their lights are still on. Open up the cupboard and see that, I run out of electricity again. Log into internet banking, buy some more tokens, type it in, and it's a bit frustrating. So I think most of you will know that on that LCD panel, there is the kilowatt hours remaining. What you may not know is that that flashing LED on the front that flashes fast when you're using a lot of electricity or slowly when you're not using much electricity, flashes at 1,000 flashes per kilowatt hour. So if you have 100 kilowatt hours on the LCD, that LED will flash 1,000 times and then it'll go down to 99 kilowatt hours remaining. So yeah, there's no APIs to these things. They're not connected to the internet. There's no user-definable plugs on the outside. So you have to do hardware hackers version of screen scraping. You have an LED that's flashing. You can buy this little sensor for 20 Rand. It's got what's called an LDR, or a light-dependent resistor. And that you can then use that little blue thing over there, a potentiometer, to change its sensitivity. So it only triggers when that LED is flashing and not when, say, you open the cupboard door or you walk past the sensor. And then it's got some output pins that then make a nice, clean square wave that you can feed into a microcontroller. The microcontroller that I'm busy using at the moment is the ESP8266. And that thing is absolutely everywhere. If you're familiar with Arduino, that's nice. That's cute. Probably want to move over to the ESP8266. It's really cheap. You can get it for like 85 Rand. It's got on its 32-bit CPU, 80 megahertz clock, 160 kilobytes RAM, 4 megs of flash, Wi-Fi, and TCP/IP. That makes it really nice for like an IoT type device, and a bunch of input and output pins and all sorts of protocols that it supports. And you'll find these inside of pretty much any home automation, from a smart bulb that you can buy from Macro to your Sonoff basic switches. They've all got this thing inside of it. It does have a bigger brother called the ESP32, which is a dual core, but I'm not really going to go into that today. So of course, I went to Communico, got myself a bunch of new toys, and wired up my sensor to the LED. So you can see at the top, there's that little white thing that's facing into the LED, and the wires coming out there, going into my dev board, and that dev board is just powered by a USB power adapter. Of course, that wasn't looking very nice, so I stuck it in a black box, wired it up to my DB board just to get some power into the thing, and there we go, got an IoT device. So the software. Demo time. Let's hope this works, please. Yeah. The first thing we do is I've got my, on the my GitHub, I've got Dale Humby DevFest 2020. I've already pulled down that repo. It's basically just a README with a bunch of instructions. So if you want to follow along, that actually I'll show you. Follow along. It's got all the instructions in there, but I'm going to do some of that demo now. First thing you want to do, we set up a virtual env called environment. This is a sandbox for Python to use, because the Python gets shipped on Mac OS is Python 2.7, and yeah, not great. So we want to activate that environment. So basically go. So you can see that it's activated because there's env, so it says I'm inside of that environment. So I want to do a pip install of ESP tool. ESP tool is a tool just for flashing the ESP8266's the firmware onto it. And I have got my chip, which is over here, which is plugged in via USB to my laptop. And how do you know which USB port is on? Well, you can go list dev, grep for USB. So basically, I'm listing all the devices that are in my device folder and go into grep or search for anything that's got USB in the title. And what I can see is TTY, W, CH, blah, blah, blah. So that's my USB device. So the next step is to put on some sort of firmware. I've chosen to use MicroPython. MicroPython, for me, I'm already very familiar with Python. MicroPython is an efficient, lean implementation of Python 3. It is a subset, so it doesn't have everything that Python 3 has, but the language is largely the same. It's designed for running on IoT devices or embedded systems, and as little as 256K of code space and 16K of RAM, you can happily run MicroPython. Yeah, you could use C or C++ or JavaScript even. And maybe in more performance applications, C and C++ is applicable, but I'm counting a flashing LED that flashes maybe twice a second. It doesn't need to be super, super fast. Okay, so now you need the binaries. So on my instructions, basically you go to get the generic ESP8266 firmware. There's a bunch of firmware here, whether you want the stable or the daily builds or whatever you want here. I'm going for just the stable, 2 megs or more, because the device that I'm using is got 8 megs. Click the file, it downloads, really small, less than a megabyte. And now we've got the binary to put on here. I'm going to copy the command. So we've already put on the ESP tool using pip install, and now I'm going to run ESP tool port, the port that we just had a look in the list command, and I'm going to erase the flash. So this takes about 15 seconds. Yeah, should be fine. Just a word of caution, this wipes absolutely anything that was on there. So operating system or files or some other language that you are running, it just completely erases it all. The only thing it keeps is the bootloader. Cool, so that worked fine. Next step is to actually put in the firmware that we got. So you've got the firmware ESP tool, the ports, same board, basically 0.5 megasecond. We're going to automatically detect the flash size, and that file, that binary that we just downloaded, we want to put on there. So that's now flashing MicroPython's runtime environment into the little dev board. And it takes a few seconds. Once that's done, should just get a success. Right, so it's done the hard reset, which means the board is ready to go. So now we've got this little board. You can see the ESP8266 on it. And on the back is the USB to serial converter that's built into the board. And yeah, so hopefully that should have Python on. I am using Screen, which is a terminal emulator, to connect to this board at baud rate 115/200. You can use PuTTY if you're on Windows, or any sort of terminal like that you want to use, Minicom or whatever. I just need something simple, so Screen. So it loads up some stuff, and we get a Python prompt. So we should be able to go, hello DevFest, and it works. And that is all running from my computer through the USB onto the little microcontroller, and that's then coming back. You may notice that stuff like exit doesn't work, doesn't understand how to get out of there. So you think, oh, I'm trapped in this thing now. Well, actually, if you go Control-A, Control backspace, and yes, you get back to the prompt, to your bash prompt. So let's go back in there, ready to do some coding. So from machine import pin, we can then make the LED, which is a pin. Pin 2 is the LED, and we want to set it to an output. And what we should do, hopefully, yes. There's a little LED that's on this board just for some debug purposes, and you should be able to see that that LED is on. I can go LED dot value, and I want to give that a value of 0. And a value of 1, that switches it off, and a value of 0 switches it on. The logic is inverted just because of the way this LED happens to be wired up, but you can see that with like 2 lines of code, you can switch an LED on and off. Similarly, you can do input. So if you go pulse pin is equal to a pin, I'm going to use 5. What I've done, in lieu of the flashing LED and all that stuff, I've just got a little push button here that I've wired up. So pin 5, I want to make it pin dot in dot pull up. So just so you understand what's happening there, the switch, the way it works is that when there's no one pressing the button, these 2 wires aren't connected together. And so that pin is floating, which means that there's a lot of noise, any sort of ambient vibrations or whatever may trigger this thing. So you switch on an internal pull-up resistor, which means that the pin should be on. So you go pulse pin dot value. We just want to do a get, and it is 1, which is, of course, if there's a pull-up resistor, it's 1. And if I, oops, don't touch the button. Sorry, try that again. Copy paste here. Sorry. Yeah, touching that with wet fingers or sweaty fingers doesn't work so nicely. Yeah, 1. Try that again. If you press the button, so I'm pressing the button now, and it should be 0, and I'll leave it alone and press it 1. What you can do is, while true, you can go pulse pin value. Should have done print pulse pin value, and it is printing 1s because I'm not pressing the button. Press the button, goes to 0, press, and so on, right? And that problem is there that it is using 100% of the CPU just to poll that pin, which is very, very wasteful, and you can't do anything else at the same time. So the next thing you can do is make an interrupt service called routine called pulse, and in this one, we just want to go print pulse detected pin ID. Yeah, and then I want to set up pulse pin dot interrupt request pulse. So I'm saying that the handler function for an interrupt service routine happens is this pulse function that it wrote. Trigger is equal to pin dot q falling. So whenever I press the button, it goes from an on to an off state, so it's a falling edge. So that's the trigger, and it will then print, call the pulse function. So I got a thing back saying it was accepted. You can see that there's nothing happening on the CPU, but when I press the button, the pulse is being detected. Now, you can also see that there's a ton of pulses being detected because this switch is what's called bouncing. It's not a perfect on and off. You can put little software routine in to debounce the switch. It's a little bit beyond the scope for right now. But yeah, you get the idea. So that's all very well. We've seen that we can switch the LED on and off. We can read from an input by either polling it or by setting up a little interrupt service routine that will then execute the code when the button is detected. But that's not much fun unless you are connected to something else. So the next thing that I want to share with you is connecting to Wi-Fi. So just on here, we've got the network that we're importing network. We're setting up a little station. We're going to switch it on. If it's not connected, it's connected to network. Test bench, and so that's the SSID and the password. While it's not connected, it just waits. And when it is connected, it prints out stuff for you. The paste mode, Control E, paste it in, then Control D to get out of paste mode, and it starts running that little bit of code that I pasted in. So connecting to network, connected, and the IP address that this device got is 10.0.0.154, the network mask, the gateway to the internet, 10.0.0.254, and 888H, which is one of the Google DNS servers. So now we have an internet connection. And to prove that, from machine import the real-time clock. I also want to import NTP time, and then so RTC is equal to RTC, NTP time dot set time. So that's going to set the time. So that's setting, calling out to the internet, setting the time, and RTC dot date time will then display the date, which is the 16th of the 10th at the 4th, which is a Friday. Monday is 0:13:44. Yeah, so now you've got the date and the time. To use the Mosquito broker from UMQTT simple import QTT client, QTT client. I was going to call this the dev board, and I'm going to connect to my broker. Got that, mqtt.connect. Now I'm connecting to the broker. Get a 0, which means success. mqtt.publish. I want to connect, publish to the topic called counter, and the string called hi DevFest. Actually spell that correctly. So before I push send there, I'm going to go to my, this is Home Assistant that I'm busy running. It's got an interface into the MQTT, and I want to subscribe to counter. Spell it correctly? Yes. So now it's busy listening. So if I click publish, you can see a message was received. That's because this Home Assistant has subscribed to the topic called counter. Yeah, next step from there is to connect that up to the pulse pin. So should be this bit of code, setting up the Wi-Fi, setting up the pins, the pull-up, which we did a little bit earlier. There's the falling edge, set up the MQTT broker, and connect to it. Now, when the pin is triggered by the falling edge, it calls the pulse function. The pulse function is an interrupt service routine, which then increments the global counter. And then what it's doing here is it's scheduling another function called MQTT publish. The reason why we're doing this is because these interrupt service routines have to be very fast. They've basically stopped the CPU from doing anything else, and you're very limited in what you can do here. Certainly you can't call out across the internet to something that takes tens or hundreds of milliseconds when this thing is expected to execute in a few microseconds. So you schedule this function to run in the background. So this is an exit, and then the microcontroller will then schedule this other thing, which then publishes the counter, turns it into a string, turns it into a UTF-8 byte encoded string, and then publishes to counter. So let's copy this. Back to, let's just reset the CPU. I'm going to paste mode, and right, so bit of code is there. If I now press the button, you can see pulses have been detected and publishing to MQTT. And if I switch back across to the topic, which is still listening on counter, you can see the count went from 1 to 3. Yeah, so Home Assistant is now getting this, the counts as the buttons are pressed. Take that one step further, and we can run a little web server. Now, the web server, once again, setting up the Wi-Fi, setting up the pins. The difference now is that we have a socket. We're opening up a socket on port 80, which is HTTP. We're listening for up to 10 concurrent connections, ready for HTTP, and now it enters this loop. It will block on accept. Once some connection comes in, some from a web browser or something, it'll print out the IP address of who's connecting, print out the debug of basically what the browser sent, and then it searches for the get and replies with 200 OK and some stuff. So let's copy and paste the code again, reset the micro, go into paste mode, and run that bit of code. Right, ready for HTTP connections. So now I have got the IP address of this ESP device, pasted into my browser, and if any luck, yes, right. Counter value is at 0. If I take this and I press the button a few times and refresh the page, goes up. Press it some more, refresh again, and that goes up. So I've showed you how to do a web browser. And this bit of code is, what, probably less than 50 lines long. And you have got a web browser. So putting that all together, I have got so my whole power meter repository is available also on my GitHub. It's got the full code. If you look at main.py, that is a pretty long piece of code because there's a lot going on, including debounce and handling errors and stuff. Go down to the web server, there's the normal get, there's a post. You can get the metrics endpoint, and then also handles 404s quite nicely. So if I go to my power meter, which is running on .11, can see that I've got 119 kilowatts remaining. I can also, when I buy electricity, type in like 3.5 or whatever it might be, click save, and it will go and save it in the EEPROM of the device, or the flash of the device. Also have a metrics endpoint, which is used by Prometheus, and it scrapes. So it's the kilowatt hours, the average power usage, how many joules I've used, and basically when this thing started up. And you can subscribe to that on something like Home Assistant. So here you can see, rather than just sending a count through, I'm actually sending some details through to that. And what happens is you can then make a nice little dashboard that says your power usage is 300 watts and 119.6 kilowatt hours remaining. You can also go and have a look at Prometheus, which has got its metrics. It's busy scanning it, scanned it 20 seconds ago. And then Prometheus, you can go and have a look at your Grafana dashboard, which is just another way of having a look at the Prometheus data, just a little bit prettier. So you can see current power usage, how much I've got remaining, and I can set alerts for when it crosses the yellow and the red boundaries, uptime, and see when my geyser is running in the morning, kettle's running for making tea and coffee and stuff. Yeah, and then of course you can tie that in with node red. So here I've got a very simple taking the power meter, which goes straight to a debug endpoint. And viewing the debug endpoint, you can see every minute there's a little payload that comes on MQTT across. Whew, okay, well, I'm glad that demo worked. Back to the slides. Yeah, showed you all of this stuff. Yeah, so my GitHub has the power meter code, and so we've got DevFest 2020 on there. You can go to the next steps, running a cluster. I'm going to go through this quite quickly. You can use something like Docker Swarm or Kubernetes. For me, we use Kubernetes at work, and that was just too much like work, so I wanted to use Docker Swarm just to learn something else. Something new on the block is lightweight Kubernetes K3s. So for those of you know that Kubernetes is sometimes abbreviated to K8s. K3s is just a bit of a play on that. That's designed specifically for embedded systems. You could network boot if you've got multiple nodes rather than running Ansible. You can just network boot them and use cluster FS, which is a redundant file system. I use it, so it doesn't matter which container my node starts up on, it will restart and find the file system that each container needs. And then you don't have to stick with Raspberry Pis. You can use stuff like the Coral AI board, or NVIDIA has the Jetson boards, both basically $100. And now you can start having like an IP camera that then streams video feed through to these boards, and you can, using TensorFlow Lite or something, start building smart alarm systems. You could track where your, I don't know, dogs or who's in your house, or you've got to have virtual fence lines. So if somebody crosses that line and it's night, then you can switch on the floodlights, or you could perhaps set off the alarm, whatever it might be, start stringing those together in more complex node-RED type scenarios. And then, of course, Google Assistant, you can then link that up through actions on Google. The downside is you do need a domain name and an SSL connection to get Google to talk back to your Raspberry Pi at home. So you need to run a reverse proxy or dynamic IP address or something like that to get that stuff into your home assistant at home. But it certainly can be done. Not going to go into that today. There are some fantastic instructions on homeassistant.io about how to link up to the Google Assistant. There's a ton of resources out there. I'm going to make this slide available on my blog, dalehumby.com. And of course, there's my GitHub, which has got the actual code. And if you get stuck, please feel free to reach out to me on email. Quick plug for my company. We're hiring. So yeah, we would love for you to come and join us.